Welcome to the last video of Thermodynamics course. In this video you're going to learn about Carnot cycle. Carnot cycle is an idealized thermodynamic cycle with the greatest thermal efficiency possible. It occurs between two isotherms and two adiabats. Let's draw its PV graph. So two isotherms, two adiabats. You can see their decreasing functions. It goes from point 1 here to point 2 to point 3, point 4 and again to point 1. We can see the cycle. The starting and ending point is point 1. Its working principle is same as for any other heat engine. So let's go through the 4 phases of the Carnot cycle. For each cycle we are going to draw a position of movable piston lid. First, from point 1 to point 2 we have isothermal expansion. Where isothermal means temperature constant, but expansion means that volume increases. So we have a piston where some gas is trapped inside and some work is done by the gas, so work is positive, and it receives some heat, so heat is positive as well. Second phase is adiabatic expansion. Where again we have some work done by the gas. This 2, 3, these indexes mean from which to which point this phase is going through. It is this very adiabatic expansion is from point 2 to point 3. So the gas does work, it is positive, and again, this heat exchange is equal to 0 because it is in definition of an adiabatic process that there is no heat exchange. And finally, work done, this W23, is minus delta U23 because we know that in an adiabatic process that a gas does work at the expense of its internal energy. We can point out this point 3 where the volume is maximum possible, so gas is maximally expanded at this point. This is V max. The third part of this process is isothermal compression, where isothermal means again constant temperature, but here is compression, so volume is decreasing. Some work is done by the environment on the gas, so it is negative, and some heat is released by the gas, so heat is as well negative as well. And now we have from point 4 to point 1, this final part of a Carnot cycle is adiabatic compression, where the gas is maximally compressed. Again, work is done by the environment on the system, so from 4W41 is negative, and heat exchange is 0 because it's adiabatic process. And as we had for adiabatic expansion, and we have for adiabatic compression, because they're both adiabatic processes, work is done at the expense of its internal energy. And finally, in point 1, the gas is maximally compressed, so it has minimum volume. So this is V min. And now we can calculate total work, total heat, and total change of internal energy in this cycle. Total work done in a Carnot cycle is sum of the 4 works done in these parts of the cycle. where the first two are positive because they are works done by a gas in its environment. So these two, 1, 2 and 2, 3 are positive, while the other two are negative because they're done by environment on the gas. And finally, work is their sum. The same or the similar thing we have it with heat, where Q12 is energy received by gas, so it is positive. Q34 is energy released by gas, so it's negative. And Q23 and Q41 are 0 because they're in a diabatic process, so there is no heat exchange. Finally, total heat is their sum, but we can write only these two, Q12 and Q34, so these from isothermal processes where some heat exchange does exist. And finally, we have that delta U, so total change of internal energy of the gas is 0, meaning that heat exchange is equal to work done, which is also true for any other thermodynamic process. So Q minus delta U, delta V is 0. There is no change of internal energy of a gas going through Carnot cycle. And it is very important to say that in all of these formulas we have pluses, but we know, because we know that, for example, these works, the work 3,4 and work 4,1 are negative, so plus times minus will be minus. But if we take that they're positive, so only their magnitude, we would have to put minus instead of plus in front of them, in front of that particular work or heat in that equation. But here we've chosen to take them as positive or negative and then put all pluses on all the places in all of these formulas. We can calculate thermal efficiency of Carnot's heat engine in the same way as it can be done for any other thermodynamic cycle. Here is the formula with parameters from the Carnot's heat engine, whose work principle is described in the example. So eta is work done in the process over heat released. Work done is equal to heat exchanged, so it is this formula for total heat done in the process, exchanged in the process over Q12, heat received by gas in the first phase, or we can write it in this way. And we also have a temperature relation for this, where TH is temperature hot and TC temperature of cold reservoir. So we can write, we've written this formula for thermal efficiency also using these temperatures. And now by using these formulas for thermal efficiency we can consider two cases in which thermal efficiency we would assume to be 0. The very first case is when both reservoirs have same temperature. So temperature of hot is equal to temperature of cold reservoir. And in this case efficiency would be 0. So eta equal to 0, because it would make no sense to have such a heat engine. And the second case, which would be the ideal, the perfect one, we could say, where temperature of cold reservoir would be 0, so absolute 0 kelvins. However, due to the fact that absolute 0 cannot be achieved, this case when eta, so thermal efficiency would be 1 or 100%, unfortunately cannot be achieved, because again we cannot achieve temperature of absolute 0. And finally we have to say that Carnot's process is really one of the most efficient thermodynamic processes, but it is hypothetical, so it is idealized. And other heat engines would have efficiency less than that of the Carnot heat engine, which is why it is so important to know about it. Just to mention, there is also reverse Carnot cycle, so reverse Carnot engine as well. This reverse Carnot engine, actually, as the name says, goes in the opposite direction. So we have a PV graph, again to isotherms, to adiabats, and it would go in this way, from 1 to 2, 2 to 3, 3 to 4, and 4 to 1. So in this counterclockwise direction. While for Carnot cycle we had clockwise direction on the graph. So it's only to indicate that it goes in the other direction. So we would have first adiabatic expansion, isothermal expansion, adiabatic compression, and finally isothermal compression, also the opposite sequence of these phases. However, this means it takes heat from cold to hot and makes it go to hot reservoir, for which a work done by environment on the gas is needed. Therefore, this cycle cannot occur spontaneously because of the outer work which has to be done on the system. So we can draw a scheme where we have again hot source, cold sink, and working body, but in this case it doesn't go from hot but from cold to hot, from cold to hot reservoir, so some work has to be done, and this is as well in the opposite direction. So some work has to be done. We can see that this scheme looks exactly opposite to that of a normal Carnot engine, so it is reverse one. There is a quantity called refrigerating effect just for this reverse heat engines, reverse Carnot engine, which can be calculated using this formula. So this refrigerating effect, which is noted with epsilon Greek letter, is proportion of heat taken from cold reservoir Q23 and work done on the gas by the environment, W. That's all for today. Now you can take a short quiz to test what you've learned in this video. You can find the link in the description of the video. Thank you for following this course on thermodynamics and for watching Science Up videos. Thanks for watching and stay with us.